Good morning, class. Welcome to today's session. Today we are going to tackle another topic, that is introduction to programming language. And here we are going to focus on writing instructions which can be used to program what Intel 8085. So in our previous session, we discussed about the introduction to Intel 8085, and we realized that Intel 8085 is like any other IC. But now the difference is that Intel 8085 can be programmed to do general purpose activities. Unlike any other IC, Intel 8085 also can perform mathematics, computation, can perform logical operations, among other things. We also realized that Intel 8085 can use up to 5 volts, which is very simple. You can only use 5 volt to power this Intel 8085. So Intel 8085 contains a total of what? 40 pins. These pins, they contain different functions. We have pins which have been grouped together to carry addresses. It's called address bus. We have pins which have been grouped together to carry control signals, which are called control bus. We have pins which have been grouped together to carry data, and they are called what? Data bus. So we have also seen that Intel 8085 can be interfaced with an external crystal clock through pin X1 and X2. So we are going to see these pins, how they are being used as we continue with our syllabus. But today we are going to focus with the programming of this IC, and we are going to see how instructions are structured, and we are going to see that we have instructions which can transfer data between the register. We have instructions which can transfer data between the memory. We have instructions which can transfer data between input-output devices. And then we have instructions which can perform control functions of the Intel 8085. Let's say we want to stop the operation of Intel 8085. Let's say I want to jump to specific instruction. We are going to see all this in this session. So make sure you watch the previous video before you progress to this one. It's very important for you to have that foundation. I also gave you some notes to complement what we discussed last time. Make sure also you write those notes. I also provided an online activity for you to showcase whether you understood the session or not. And I provided some simple questions. It was about a total of 7 questions. So you are supposed to do those questions. I'll share the results with you in the course of today. So welcome to this lecture, and feel free to pause whenever you are not understanding it. And this is an advantage of having an online session, especially the video, because you can go back and forth when you don't get something. So relax and let us begin. So at the end of this session, we are supposed to be able to tackle the following objectives. First of all, you are supposed to describe what is a machine cycle. You are supposed to explain an instruction format. You are supposed to describe data transfer instruction in programming. You are supposed to describe the instruction in data manipulation group. You are supposed to describe the input-output instructions. You are supposed to describe the machine control instructions. You are supposed to describe transfer of control instructions in programming. And then explain the need and the use of assembly directives. Those are going to be tackled in this session. And then in the part 2 of this session, which is still in this topic, that is the introduction to assembly language programming, we are going to tackle various addressing modes, and then we are going to do some application of programs. We are going to write some simple programs. So that's what we are supposed to tackle in this topic. So this topic is going to be covered in 2 sessions. Part 1, which is this session, is going to cover the first objective to the objective from objective A to objective H, and then in the next session we are going to cover objective I and J. So anytime the microprocessor is carrying out a task, that task is broken down into subtasks. What I'm trying to say that a microprocessor will always follow some small steps to achieve or to complete a task. So the sequence of operation that a processor has to carry out while executing the instruction is called instruction cycle. Each instruction cycle of a processor in turn consists of a number of machine cycles. The machine cycles are the basic operations performed by the processor. To execute an instruction, the processor executes one or more machine cycles in a particular sequence. The machine cycles of a processor are called processor cycles. So the manufacturer of microprocessors define the timings and status of various signals during processor cycles. You have to understand that a microprocessor will always carry out activities in a timing manner. So everything which we do with the microprocessor, or what the microprocessor does, all activities has to be timed. And how do we time these activities? We use what is called cycles. So cycles are signals. These are signal which is being generated by what? By a crystal oscillator. It's a signal which contains a rising edge and a falling edge. This signal is generated by what? A clock, which is normally referred to as crystal oscillator. And these one are used to guide the microprocessor, to do the timing functions of the microprocessor in order for the microprocessor to carry out its operation. So this clock signal is the one which we call what? Cycles. Refer this as what? As a rising and falling of the sun. So for example, human being and most of the creatures in this world, we are governed by the natural clock. This natural clock is the sun. When the sun rises, we have activities which we are supposed to do up to the time which the sun falls. So ikifika asubuhi tunafanya shughuli, ikifika jioni tunaacha hiyo shughuli, maybe tunafanya shughuli ingine, and the activity repeats itself. Let's say if I want to send you to your uncle, of course you will not go during the night. You will say you will go early in the morning. So when it reaches early in the morning, you prepare yourself, you go to your uncle. Why are you doing that? You are doing that because you've been governed by a natural clock, which is sun. You saw it that it's better for you to travel during the day and not during the night. For example, another example is when we wake up early in the morning, then we go to school. So if you want to attend a lesson, you have to come during the day, but you cannot come during the night and you want to attend that lesson. It means that you will be out of sync. So the microprocessor and the microcomputer environment, they use this clock signal to govern its and other operations inside the microcomputer environment. So we've said the manufacturer is going to provide what is called timing signals, and the timing signals looks like this, what we have here. So we have an example of timing signal here. This one is a clock signal which is generated by the crystal oscillator. We have the rising edge and we have the falling edge. We have the T on and the T off. So if I measure from one falling edge to the next falling edge, that is one complete period, and that is equivalent to one T state. Yeah. So this one is also like the natural clock, which is sun. So we have the time which the sun is rising. This when you can time the sun and do activities. So this when we wake up, we prepare ourselves, and then we do activity for the time which the sun is on, and then when the sun is falling, we prepare to wind up the activities which we've been doing during the day, and then we go to sleep, and then we continue this way. So if I wanted to read a data from the memory, this clock signal also is going to govern not only the microprocessor but also the memory. Let's say at this rising edge, the microprocessor can provide address of the memory location where we want to fetch data. During this T on, the memory now puts the data which was requested by the microprocessor, and the microprocessor reads that data. And then during the falling edge, the microprocessor and the memory, they wind up that activity. If that was not performed during this period, we can time it in the next rising edge. Yeah, so it's the same as, let's say you are supposed to go to the farm and then you never went to the farm, so you can wait for the next day, you go to the farm, but you cannot decide to go to the farm during what? The night. So this is very, very important. That's why we say it's a timing signal. So the processor takes a definite time to execute the machine cycles. The time taken by the processor to execute a machine cycle is expressed in T states. So one T state is equivalent to the time period of the internal clock signal of the processor. The T state starts at the falling edge of a clock. So we are being told that microprocessor will take a definite time to execute a machine cycle, and that definite time we normally measure it in terms of what? T state is a period for a complete oscillation. But now this T state is measured from what? Falling edge to the next falling edge. I think this is very, very important, and this is complete one period. So we have some small note to take, that the time which is period is equals to T, which is our T state, which is equivalent to 1 all over F, where F is the internal clock frequency. And this is where you understand now, the faster the microprocessor, the faster we can carry out our process, because processor with higher frequency tends to carry out a lot of activities within a short period of time. And it means that if we have a high frequency, then our T state is going to be very, very small, because T is inversely proportional to what? To the frequency. So the higher the frequency, the lower the T state. I think this is very, very important. Now, for just to give you here a hint, remember our modern microprocessor will run at higher speed. Their clock frequency are in terms of 3.4 gigahertz, which is very, very, very fast, not compared to Intel 885, which used to run at clock frequency of less than what? 88 MHz. So machine cycles, machine cycles are grouped into different categories. We have machine cycle for fetching opcode. We have machine cycle for reading memory. We have machine cycle for writing memory. We have machine cycle for reading input-output devices. We have machine cycle for writing input-output devices. And then we have machine cycle to acknowledge and interrupt. So for opcode machine cycles, this is the most basic cycle and always the first one in the instruction. The CPU generates the control signal to read the next instruction. Opcode, the part of the instruction that specifies the operation to be performed, like add or subtract from memory and load it into instruction register. So here we are being told that this is the first machine cycles which is going to be executed always by the microprocessor. And this one is when we want to fetch what is called opcodes. Opcodes, these are control instructions which tells the microprocessor what to do. For example, add, subtract, yeah, um, and or move. Those are different opcode instructions. And then we have what is called memory read cycles. This cycle is used to read data from a specific memory location. The CPU places memory address on the address bus, sets the read signal, and then waits for the data to be placed on the data bus by the memory controller. And then if you want to write data to the memory, is the opposite of reading the memory. This cycle writes data to a specific memory location. The CPU places the memory address and the data on their respective buses, then activates the write signal. And then we have the one for input output read and the one for input output write. This is the same as memory read or memory write, but it's only that we are talking about input output devices. This is similar to a memory read, but it's used for an input output device. The CPU generates control signal to read data from a device such as keyboard or a network card. And then we have interrupt acknowledge cycles. These are machine cycles which are very special cycle. Is used to acknowledge an interrupt request from an input output device. Remember, the microprocessor can be interrupted by the input output devices when they want to exchange data. If that device is going to interrupt the microprocessor has to answer with what? Interrupt acknowledge for the data to be exchanged. So that interrupt acknowledge has special what? Machine cycles under what is called interrupt acknowledge. So we have an example here. I'm moving data from register B to register A. So how many cycles do I need to accomplish this? I only need one machine cycle, and that machine cycle is going to be what? Opcode Fetch machine cycles. So we can have other examples of storing data to the memory, reading data from the memory, writing data to the memory, among other examples, which we are going to see as we continue. For us to better understand the instruction of Intel 885, we have to understand how the instructions are formatted. So instruction is made up of two main parts, the opcode and the operand. But it doesn't mean that all the instructions contain operand. I want you to understand that. So when we have an instruction which contains opcode and operand, then it means that the opcode is going to occupy 8-bit and the operand is going to occupy 8-bit to 16-bit. But if I have an instruction which only contains an opcode, then that instruction is going to be 8-bit in length. So what does this mean? It means that the smallest instruction you can get is an 8-bit instruction, and that instruction is going to contain what? Only opcode. Instructions which are 16-bit to 32-bit in length, then it means that this instruction contains both opcode and operand. Opcode is the instruction itself, like move, increment. Those are the opcode. Is the muscle part of the instruction, and then operand is the data which we are working using that instruction. Let's say if I want to move 2, which is a number 2 as decimal from memory to the register, then I'm going to use what is called move instruction. So MOV, that move is going to be part of what? Part of the opcode. And then the number 2 is going to be our operand. So we can use this as an example also. We have MVIA. This one is the opcode. 32 is what? Is the operand. This is the data which I'm working on. Now, 1 byte, that is 8-bit, only opcode is going to appear this way. So we have an instruction which is INRA, yeah. And in that instruction, we are going only to have an opcode. Then we have a 2-byte opcode plus 8-bit data. So this is a 2-byte instruction. A 2-byte instruction is a 16-bit data. Remember, 8-bit forms 1 byte. So 2 byte is equivalent to 16-bit. So if I have a 16-bit instruction, 8-bit is going to be what? The opcode. Another 8-bit is going to be the operand. And this is the instruction. And then we have a 3-byte, that is opcode, which is 8-bit plus 16-bit address. This one, e.g., we are loading memory location, data in this memory location 2050H to the accumulator. So 2050H is a very big number. It's an address, but a very big number. So we have to break this address into higher byte and lower byte. So the higher byte is going to be 8-bit, the lower byte is going to be 8-bit. That forms what? 16-bit address. And then we have what? Our opcode, which is LDA, which is 8-bit, which makes this instruction to be what? 3-byte or 24-bit length. So those are the instruction format. In summary, instruction format can either be opcode or opcode plus operand. If the instruction is only opcode, then it's 8-bit in length. If that instruction contains opcode and the operand, then it's going to be 16-bit in length or 24-bit in length, which means that the opcode is going to maintain the 8-bit and the rest is going to be for the operand. The bigger the address, the more location is going, the more memory location is going to occupy. And that's, for example, we have a very big memory address here, 2050H, which we have to break it into upper byte and lower byte. We are going to see this as we continue. Don't worry. I want us now to look at our first type of data transfer, our first type of instruction, which is data transfer instruction. So data transfer instruction moves data without changing it. When we want to move data without changing it, then we use what is called data transfer instructions. They are used to exchange data between the registers, or between the register and the memory, or between the memory and input-output devices. This is very important. You understand that. So we have different examples here. We have an instruction where we are moving data from register B to register A. This one is move A, B. So you copy register B into A. Not copying the register, but the content of what? Of the register. And then we have MVI C. So when you see MVI, any instruction which ends with I, remember that you are working on the data, but that data is not found in any location. This data is just found inside your mind, but you want to load it directly to the computer. So sometimes you have things which are in your mind, they are not stored anywhere in the computer, but you want to load it directly to the computer. So we use this instruction, MVI, LDI. When you see this type of instruction, know that what you are talking about here is the data which is not found anywhere, but inside your thought. For example, here, I'm loading data which is 32 hexadecimal number to a register C. So I'm loading 32H into register C. And then I have LDA. I told you LDA is when we want to load accumulator with the data from a memory location. But if I wanted to load the accumulator with the data which is not found anywhere, then this instruction will change from LDA to LDI. And then this here is not going to be the address, it's going to be the data itself. Anyway, don't worry, those are going to be clear as we continue. So I have memory location 2050H which contains a data, and that data is going to be loaded to what? To the accumulator. So load from memory location 2050H. And if I want to load data from the accumulator to a memory location, then I have to use a store instruction. So we have STA, so STA 3050H. So I'm storing data from the accumulator to memory location what? 3050H. Store A into memory 3050H. And I have a good illustration here of what is happening. For example, I have a simple instruction here whereby MVI, I told you MVI is you are loading data which is 8-bit data to a register RD. So RD is the destination register. And what does this instruction accomplishes? This instruction accomplishes whereby we are going to load a data which is 8-bit to register D. This register D can be either B, A, B, C, D, E, H or L. So you can see how these examples is achieved. So we have an example here. I'm loading data MVI to register D, and this data is 09H. So 09H, which is an hexadecimal number, is going to be stored to register D at the end of this instruction. And you've seen before in register D we have maybe C2, and after the execution in register D we are going to have 09H as an hexadecimal number. What you are seeing here, these are the machine cycles which we are going to execute for us to carry out this or for us to finalize on this instruction. So we are going to have a total of 4T for fetching the opcode. Then we are going to have 3T for memory read. We are going to take a total of what? 7T. Other instructions which are similar to this one can be MV to the accumulator, MVI to register B, C, D, if you up to the L. So I think that is well understood. So apart from data transfer instructions, we also have data manipulation instructions. These are instructions which can be used to manipulate what? Data. For example, you can do addition of data. We can compare numbers using the logical operation. Yeah, we can multiply numbers. We can subtract numbers, among other things. So that is called what? Data manipulation instruction. They are categorized into two. We have arithmetic operations, arithmetic instruction, and then we have logical instructions. For example, we have add B, subtract C, increment D, decrement E. So you know the work of incrementing and decrementing. So incrementing, it means that the data which is inside D can be incremented by 1. And the decrementing E, it means that the data which is found in register E can be reduced by 1. We can subtract what is inside the accumulator by what is inside what? Register C. We can add what is inside the accumulator with what is inside register B. And then we have logical operations here, my instructions. NA, we have XRAL, we have CMP, and then we have CPI. Those are few listed what? Logical operations. So this one is when we want to do AND operation. This one we want to do XOR operation. This one we want to compare our data. This one is like we are comparing what is inside the accumulator with what is inside the memory. So we have an example here. We are add m. Add m is a good example. So what we are adding to the accumulator with what is found inside memory m. M is memory location. And we have an illustration here. We are going to take what is inside the memory location, add to what is inside the accumulator, and then store the results in the accumulator. That can be achieved by this instruction. Or sometimes also we can have a data which is being held by register pair HL. We can add them to what is inside the accumulator and then store the results inside the accumulator. This is when we are doing what is called indirect addressing, and then this is when we are doing what is called memory addressing, direct addressing. This is direct addressing, this is indirect addressing. We are going to see them in our second session. We have an example here. Let the content of accumulator, so inside our accumulator we have a content which is what, 44H, and then we have content in memory location 73H, in location C00AH to be what, 73H. So we have 44H and 73H hexadecimal number. So the content of memory location, which is this one, is going to be added to the accumulator, which is register A. The results is going to be stored back to the accumulator. So this is before execution, and this is after execution. So before execution, our accumulator ilikuwa na 44H. Our register pair, and this is when I was telling you when we do what is called indirect addressing here. So we are holding our address of memory location in the register pair HL. This is very complex, but don't worry. As we will meet and then we'll discuss this part. Normally it confuses our trainees when you hold the address of memory location in the register pair. So now if you expound this address in terms of what, if you expound this address, we are going to have what is called the upper byte and lower byte. So if you go to memory location, we have COOA, and that memory location contains what, 73, which is our data. So during the addition, this is what is going to be performed. We are going to get a sum which is 87, and then we don't have a carry. This is going to be done by the the arithmetic logic unit. So we have a functional block inside the microprocessor which is going to carry out arithmetic operation, and it's called what, ALU. Then after execution, our data inside accumulator is going to be what, B7. So this one, when we convert this binary number into hexadecimal, we get B7. So after execution, we are going to have what, B7 as our data inside what, accumulator. How many cycles we are going to use? Those are the total of the cycles we are going to use to carry out this instruction. In short, I don't want you to complicate yourself. Just understand that data manipulation instructions can be used to add, subtract, increment, decrement, and XOR, compare, among other instructions. These instructions are used to manipulate data. We can add what is inside the register to what is inside the accumulator. We can subtract what is inside the register with what is inside from what is inside the accumulator. We can increase the data inside D by 1. We can reduce the data inside E by 1. I will share with you the list of all these instructions and their meanings, so don't worry. So another type of instructions are instructions for reading data from input-output devices. So these are called input-output instructions. So if I'm reading data from an input device, then I will have to use what? In. If I'm writing data to an output device, then I have to use what? Out. You remember, input output devices are going to be interfaced to your microprocessor through what is called ports. These ports are going to be assigned addresses. So if I'm reading data from a port which contains a certain address, then it's going to be in port address. So read from input port into accumulator. And then if I want to store data to a port and that port contains an address, then it's going to be out that address of the port. So this one is going to send accumulator contents to output port. What does this tells you? It tells you that these instructions are always useful when you want to exchange data from the accumulator to the input-output devices. We have an example here. We have an in 01H, then we have out 02H. So 01H is the address of the port. So we are reading data from the input port, which is address 01H. And then if I want to write data to an output port, then I'll use this instruction, out 02H. 02H being the address of the port. So we have another example here. So you'll go through this example. Let's say if I want to if I want to transfer a data which is found in an 8-bit address to the accumulator, then I will use this instruction, in address 8-bit. And at the end of that execution, I'm going to use how many cycles? 10 T cycles. So the same thing with what? If I want to write data to an output port, so that data is going to move from the accumulator to the port address of the output device. We have a small note here to take. In an 8085 processor based system, when the input-output device are mapped by the input-output mapping, then the processor can communicate with those input-output devices only by using in and out instructions. The processor uses an 8-bit address to select input-output mapped input-output devices. With 8-bit address, the processor can generate 2 raised to 8 addresses, which is equivalent to 256 bits of addresses. These are going to be assigned to input-output devices. Just to summarize this part, remember that sometimes we want to exchange data between our microprocessor and the outside world. Those outside world are what is we called input-output devices. The only way we can interface an input-output devices to the microprocessor is to use what is called ports. These ports are going to be assigned addresses by the microprocessor, and we are being told microprocessor will use up to 8-bit address for these ports. So if you want to know how many addresses you can get, you will just have to do simple calculation. So it's 2 raised to 8. Why are we saying 2 raised to 8? Because it's a binary number. A binary number can either be 0 or 1. It contains only 2 states. So it's 2 raised to 8, which is 256 addresses. It's very small for the input-output devices. But for the memory, remember this goes up to 2 raised to 16, which is 64 what? KB. Very big number. So another group of instructions are what is called machine control instructions. These instructions are used to control the microprocessor. So we've seen we have instructions which can transfer data. We have instructions which can manipulate data. We have instructions which can move data between input and output devices and the microprocessor. And then we have instructions which can just control the microprocessor. So for example, we have some few examples here. We have NOP, that is NOP, we have halt, we have di, and then we have ei. So if I want to stop execution of any operation, then I can use NOP instruction. This one will force the microprocessor not to execute any instruction or any operation. If I want to stop execution of the instruction, let's say I have an instruction, and then at the end of that instruction, I want to stop the microprocessor from continuing with the execution of that instruction, then I will use what is called halt. So ni sana nimekuambia nimekutuma uniletee maji ya kunywa, then umeenda umeleta hiyo maji, umesimama nayo hapo hivyo, na mimi sijachukua hiyo maji. So of course umeenda umeleta maji, but sijachukua maji, so inamaanisha sijakunywa maji. So wote tumekuwa kwa suspend mode. We can stay that way forever. So for that process to complete, if I have sent you for water, then you've brought that water, and then I have to take that water from your hands, and then I drink them, so that I will release you to go and do other things. Also in microprocessor, you cannot just execute the instruction and then suspend that instruction without actually stopping the microprocessor. You will be making the microprocessor to be in suspend mode. It's like it is executing the instruction, but the instruction has already been executed. So for you to end that process so that the microprocessor will do other things, you have to use what is called halt instruction at the end of every program you are building. This one will stop the microprocessor from executing further beyond what you need. So if you want to disable interrupts, you can use DI. If you want to enable interrupts, you can use EI. So I have provided here some examples for you to check them further for you to understand how are they used. So another group of instruction are called transfer of control instructions. These instructions are used to control the microprocessor how to handle what? The instruction. So you can force the microprocessor to jump to a specific instruction location. So let's say I was doing this. We can use an example. Which example can we use in real world? Let's say you are doing a certain task at the farm, and then the lunch is ready. So someone will call you for lunch. Let's say your mom. Say, hey, lunch is ready, come and eat, so that you'll go back to what you are doing. So that one is forcing you to leave what you are currently executing and then jump to another instruction. So this instruction which you are going to jump to is taking lunch. You'll go and take lunch, and then you'll come back and continue with what? The rest of the instruction. So when you want the microprocessor to jump to a specific instruction, then you use GMP. This one is the memory location of where you want that instruction to be executed. Now this is a conditional jump. It means that we don't have any condition for us to jump. Then we can jump if 0, JZ if 0 to memory location. This one we can call a subroutine. Subroutine is a small instruction which can be executed when executing the main program. Sometimes we need to complement the main program using other small instructions which are stored maybe somewhere in the memory. Let's say you are browsing the internet using your Firefox browser, and then you downloaded a music, and then you want to play that music. The Firefox does not contain mechanism to play the music. So when you click the file which you've downloaded, the Firefox will ask you which application are you going to use to play music. So it will display list of applications for you which are going to handle that file. So you will see music player, VLC player, among other media players. So when you select one, you are forcing the microprocessor to call a subroutine, to call another instruction, another program which is not part of the main program. So the main program maybe is the Firefox, But the subroutine which you are calling is another program which is going to play that music. So you will open that music, you will play. After the end of the music, that subroutine is going to be executed to the end. So after executing the subroutine, we go back to the main program. So after playing the music, now you'll see you go back to the Firefox browser, and then we can return to the main program. So let's say you jump to the unconditional jump, then you want to return back, then you use this return. And then we have another group of instructions which are called assembler directive instruction. These instructions are not executed by the CPU, but they are being used to guide what? The assembler. So it's only for guiding what? The assembler. So we can set the origin of the, or we can set the starting address. Let's say if you want the address to start from 2000H going forward, then you can set the original address to be 2000H. Set the starting address. And then DB8.2. So when you want to define a data, we use this instruction. So you can define a data to be 8-bit, you can define a data to be 16-bit or 32-bit. We can even reserve some bits using this instruction, and then we can even end the program using the end instruction. So these cannot be executed by the CPU, but they are here to guide the assembler. So we've come to the end of this session. I told you that this session is going to be broken down into two sessions. This topic is going to be broken down into two sessions. So the first session we've discussed actually how the instruction is built, and we see that for us to have a program, programs are made of what? Instructions. I think that's the right statement. Programs are made of what? Instructions. Instructions are building blocks of what? Programs. An instruction can either be 8-bit, which means it contains only an opcode, can be a 16-bit, which means contains an opcode and the operand, or it can be a 24-bit, which means contain an 8-bit opcode and a 16-bit operand. We've also thus see that for the microprocessor to execute an instruction, it has to break that instruction into machine cycles. And we've seen that we have machine cycle for fetching the opcode, we have machine cycle for reading memory, we have machine cycles for writing memory, we have machine cycle for reading input-output devices, we have machine cycle for writing input-output devices, among others. So a machine cycle is set of what? Clock signal. So for the microprocessor to execute a machine cycle, several clock signals are going to be used, and we saw that a clock signal contains a rising edge and a falling edge. For us to measure one period of the clock signal, we measure from the falling edge to the next falling edge, and that period is the same as one t-state. So one instruction is going to use several machine cycles to be executed. Those machine cycles are made of what? T-states. T-states is inversely proportional to the frequency of the clock signal. So the higher the frequency, the shorter the T-cycles. What does this mean? It means that the higher the frequency, the shorter the time the microprocessor is going to take to execute what? An instruction. And we've seen that. We've also learned formats and a group of instructions. We've seen that we have instruction for transferring data, we have instruction for manipulating data, we have instruction for reading data from input-output devices, we have control instructions, among others. So in our next lesson, we are going to see different addressing modes of these instructions. Remember, we have instructions which can move only data between the registers. We are going to see that we have instructions which can be used to move data between memory and memory, or memory and what, register. We are going to see that we have instructions which can be used to exchange data between input output device and a memory. And we are going to see how these instructions are used to do addressing of different devices inside the microprocessor. And then at the end of that, we are going to see applications of these instructions. Otherwise, ladies and gentlemen, this comes to the end of the session. This is the second session of our online training. I told you that we'll be doing blended learning. Blended learning is whereby some of the lessons are going to be online, others are going to be physical. I recorded the first lesson for you. Make sure you watch that video before you proceed to this video. There are some activities which are shared with you. Make sure also you work on those activities. Otherwise, I don't have anything to add. If you have any question or concern, please you can reach out through me, through my number. The class rep has my number, so you can always reach out to me. Again, there is something which I want you to understand, that these videos are very, very important because you can use them to train yourself. You can move back and forth, you can pause, you can do any other things. You are free to do that. I'm going to provide some follow-up activities, so be ready for any activity which is going to come on your way. Otherwise, enjoy your day. We'll meet on Thursday.